Hello everybody, welcome back to my YouTube channel. I, JSS, bearing the USN 1VE21CS064, am here today to take over the subject Mathematical Foundations for Computing Probability and Statistics. So let us get into the topic. The topic today I am going to be discussing about is going to be the applications of Gauss divergence. But before understanding the applications of Gauss divergence, we must understand what do you mean by Gauss divergence. So Gauss divergence of a vector field is a fundamental concept in vector calculus, and it has various applications in physics, engineering as well as mathematics. Here are just some of the applications of the divergence, or rather the Gauss divergence theorem, in different fields. So the first one being electromagnetism. In electromagnetism, Gauss's divergence theorem is used to relate the behavior of an electric and magnetic field to the charge as well as the current distribution. It is employed to derive the Maxwell's equation and is essential tool for understanding the behavior of electric as well as magnetic fields in different systems. Moving on to the next slide, we have fluid mechanics. In fluid mechanics, or rather in fluid dynamics, the divergence theorem as a whole is used to analyze the flow of fluids and relate the behavior of a fluid field to the source and the sink of fluid quantities. It plays a very crucial role in the study of fluid flow, conversational laws, and the development of various fluid flow equations, such as the continuity equation and the Navier-Stokes equation. The next point being heat transfer. The divergence theorem is utilized in the study of heat transfer phenomena such as conduction, convection, and radiation. It helps in understanding the heat flow within a system and also helps in analyzing the temperature distribution and determining the heat source or the sink. The next point being mathematical analysis. The divergence theorem has significant applications in mathematical analysis, particularly in the study of partial differential equations, or PDEs. It is used to convert volume integrals of divergence terms into the surface integrals, which can simplify the analysis of PDEs and lead to the derivation of various mathematical results and theorems. Moving on to the next slide, we have conversation laws. So the divergence theorem is closely related to the concept of conversational laws in physics. By applying the divergence theorem to the flux of a conserved quantity, example is mass, energy, or rather momentum, one can relate the rate of change of the quantity within a region to the flux across its boundary. This allows for the formulation of important conversation equations in various fields such as the mass conservation, energy conservation, and the conservation of linear momentum. Next point being computational physics and engineering. The divergence theorem is going to be extensively employed in numerical methods and computational techniques for solving complex physical and engineering problems. It is often utilized to transform the volume integrals into surface integrals, allowing for the development of efficient algorithms for numerical solutions and for the computational modeling. Moving on to the next slide. Computational physics and engineering. The divergence theorem is extensively employed in numerical methods and computational techniques for solving complex physical and engineering problems and is often utilized to transform the volume integrals into surface integrals, allowing for the development of efficient algorithms for numerical simulations and computational modeling. These are just a few examples of the numerous applications of Gauss's divergence theorem. Its versatility and importance in various scientific and engineering disciplines make it a fundamental concept for understanding and analyzing the physical phenomena. Moving on to the next slide. While Gauss's divergence theorem is primarily applied in physics and mathematics, it is also going to find its application in computer science and engineering backgrounds. Here are the few areas where the concept of divergence theorem is going to be relevant. The following are going to be the applications in the CSE stream. The first one being computational fluid dynamics, or CFD. So computational fluid dynamics is extensively used in engineering simulations to understand the fluid flow and related phenomena. The divergence theorem plays a very crucial role in discretizing and solving the governing equations of fluid flow, such as the Navier-Stokes equation. It allows for the formulation and the numerical methods, such as finite volume or finite element methods, by converting volume integrals of divergence terms into surface integrals. This enables the accurate computation of flow properties and the behavior of fluid fields within a computational domain. Moving on to the next slide, we have computer graphics and visualization. In computer graphics and visualization, the divergence theorem is employed for vector field analysis visualization. Vector fields can be represented in various physical quantities such as velocity, force, or rather electric fields. By computing the divergence of vector field, one can identify the regions of expansion or contraction within the field. This information is valuable for visualizing the flow pattern and analyzing the vector field data and creating realistic simulations of fluid dynamics or other physical phenomena. Image processing and computer vision. So the concept of divergence is utilized in image processing and computer visual algorithms. Divergence based operators such as the gradient of an image or the Laplacian operator are employed for tasks like edge detection, image segmentation, and feature extraction. These operators measure variations or changes in intensity across an image and help identify the significant regions or the boundaries within the image. The next point being optimization and machine learning. Divergence is utilized in optimization of algorithms and machine learning techniques. Divergence measures such as the KL divergence are employed in probabilistic models and optimization problems to quantify the dissimilarity or rather the difference between the probability distribution. These measures are used in various applications such as the clustering classification, information retrieval, and generative modeling. Moving on to the next slide, we have computer simulations and finite element analysis or FEA. Divergence plays a very important role in computer simulations and FEA, that is computer simulations and finite element analysis, for solving a wide range of engineering problems. In structural analysis, for example, the divergence theorem can be used to relate the internal forces within a solid to the surface transactions applied on its boundary. This allows for the formulation of finite element equations and the computations of stress and deformation distributions within a solid structure itself. These are just a few examples illustrating how the concept of divergence, as encapsulated in Gauss's divergence theorem, has applications in computer science and engineering. By leveraging the fundamental principles of vector calculus, divergence aids in the analysis, simulation, and optimization of various systems and processes in these fields. I hope you understood a lot about the applications of Gauss divergence, what is Gauss divergence, and the applications of Gauss divergence in the CSE background or rather the CSE stream. Thank you for watching the video.